Infinity. It's a word we use casually, and almost always incorrectly. We say things are infinitely small, or that someone has infinite patience. But what is infinity really? And could something be larger than infinite? Tonight, as you drift further into stillness, we'll explore a number that shouldn't exist, because it dares to be more than forever. Let's begin simply. Imagine counting. 1, 2, 3, keep going. Never stop. Eventually you'll reach a number so large it has no end. Infinity. It's not a number exactly. It's more of a concept, an idea that captures endlessness. In math, we call this kind of infinity countable. It's the infinity of natural numbers, the kind you can, in theory, reach by adding 1, again and again, forever. It's already unsettling, but it's only the beginning. Now, imagine a different kind of infinity, not made of whole numbers, but of points. Between 0 and 1, there are an infinite number of decimals. You can divide that space endlessly. 10 parts, 100, 1,000. Keep slicing. Every slice contains another infinity of smaller parts. This new kind of infinity is actually larger than the first one. Yes, there are different sizes of infinity. A bigger infinity, a number greater than forever. This was the discovery of a mathematician named Georg Cantor. In the late 1800s, he asked a dangerous question. Can we count all real numbers? Not just the ones we know, like 1 and 2, or even pi, and the square root of 2, but every number that could possibly exist on the number line. He tried, and failed, because it turns out, between any two numbers, there are infinitely more numbers than in the entire set of whole numbers. It's like this. If you think of infinity as a hotel with an endless number of rooms, whole numbers can each check into their own room. But the real numbers, they flood in like an ocean, and there aren't enough rooms. Not even in an infinite hotel. This new size of infinity is uncountable. It's not just longer, it's denser, more infinite than the infinity before. So Cantor gave it a name. He called the original infinity Aleph Null, and the next one, the bigger one, he called the continuum. It's the size of all real numbers. And yes, it's infinite, but it's more infinite than the first. Let that settle in. There's not just one infinity. There are layers, hierarchies, an endless tower of infinities, each one bigger than the last. It's not just forever, it's forever. Plus, you may ask, how is that possible? How can something be bigger than everything? The unsettling truth is infinity is not the ceiling. It's the floor, and above it stretch levels of reality. Our minds were never built to climb. Each new level contains more than the one before. More numbers, more possibilities, more paradoxes, and we're only at the second floor. Mathematicians suspect there are infinities so large, so abstract, that even our systems of logic can't contain them. Some infinities are so large, they can't even be named without breaking math itself. These numbers shouldn't exist, but they do. They exist as shadows behind the symbols we use. They whisper from the corners of logic. You can't see them, but you can feel their presence. They remind us that no matter how far we reach, there is always more, not just beyond, but within. Infinity is not the end. It is the beginning of something stranger, something impossible to finish, and perhaps, something impossible to truly begin. As you drift, think of this. Some numbers lie beyond the horizon of thought. They wait in silence, not because they are hiding, but because we are still learning how to listen. Infinity is not one thing. It is a ladder with no bottom, and no top. A staircase that folds into itself, a number that opens the door to numbers that shouldn't exist, and then steps through it. Now, from this infinite staircase, we descend into something darker, a number so unstable, it threatens to unravel the very fabric of logic. A number that says I should be everything, but I am nothing. Close your eyes and picture a line. A number line. Simple, straight, endless in both directions. Every point on this line holds a value, a number, nestled perfectly in its place. Some are whole, 1, 2, 3. Some are fractions, 1/2, 1/3, 100 over 1,000. We imagine this line as complete, every value accounted for. But there's something hiding between the cracks. A number that's there, and not there. Tonight, we visit the number that's real, but never reachable. Imagine walking from 0 to 1, step by step. First you go halfway, then halfway again, then again. You keep getting closer to 1, but you never quite touch it. It's a classic thought experiment, an infinite regression, and it feels a little strange, but eventually, you understand, even though it takes infinite steps, they get smaller and smaller, and in the end you arrive. 1 is there, solid, real. But now, let's imagine something harder. You're looking for a number that isn't rational. That is, it can't be written as a simple fraction. No matter how hard you try, take the square root of 2. You can estimate it. You can get very, very close. 1.4, 1.41, 1.4142, but you'll never land on it exactly. Its decimal never ends, and never repeats. It goes on, into the dark forever. You might think, that's fine. We can live with that. We'll just use better approximations. But here's the catch. No matter how good your guess is, it will never equal the real thing. It's like chasing a ghost across the number line. You get closer, you think you see it. But when you reach out, there's nothing. These numbers are called irrational. But not because they're crazy. They're irrational because they cannot be expressed by the tools we usually trust. Fractions, ratios, clean divisions. Now imagine a number even more elusive. A number that hides not just from fractions, but from everything. Even our most precise machines, most powerful calculations, can never hold it. You can write 1,000,000 digits of it, 1,000,000,000. But the real number, the full, perfect version, will always be out of reach. It will always live just one step beyond your last attempt. That's the kind of number we're talking about tonight. A number that is real, meaning it lies somewhere on the number line. You could point at it. In theory, you could say, there, between these two numbers, but you could never write it, never finish it, never catch it. It lives in a shadow realm between precision and impossibility. This kind of number raises a question. Can something be real if we can never truly touch it? It's not imaginary. It's not theoretical. It's there, as real as 1 or 2 or 3. But no human, no computer, will ever fully know it. We can circle it, estimate it, name it, but it will never reveal itself in full. Some of these numbers are so specific, so unrepeatable, that they have no pattern at all. Each digit unfolds like static, no rhythm, no cycle, only chaos. And yet, this chaos lives quietly on the number line, perfectly still, perfectly placed. This contradiction, of being fully real, yet forever unreachable, is what makes these numbers so disturbing. They shouldn't exist in any meaningful way, but they do. They shape the curves of our universe. They appear in geometry, in physics, in music, in the timing of the stars. They are everywhere, and nowhere. Numbers like pi, the square root of 2, the golden ratio, these are just the beginning. There are infinitely more irrational numbers. In fact, most numbers are irrational. Let that sink in. Most numbers that exist are numbers we can never actually write down, never fully grasp, never contain. You might be falling asleep already, gently floating through that endless space of real numbers. But before you drift too far, let this truth echo once more. Some numbers are real, but they will never let you find them. They hide not out of cruelty, but because reality itself is deeper than our language, more infinite than our tools, more mysterious than our minds. Now, from unreachable numbers, we turn toward the void, a mathematical monster so strange, it feeds on infinity, and grows larger than forever. There's a quiet kind of number that doesn't play by the rules. It doesn't scream. It doesn't break systems the way infinite numbers or paradoxes might. Instead, it whispers. It tells you one thing, and then makes that thing untrue. Tonight, we meet a number that lies. A number born from contradiction, forged in paradox. It's called the liar's number, and it lives in the shadows between truth and falsehood. Let's begin with a sentence. Simple, short. This statement is false. Read it once, and it's a little odd. Read it again, and you realize you're stuck. If the sentence is true, then what it says must be the case. but it says it's false, which means it's not true. But if it's false, then the sentence is wrong, which would make it true. And so, round and round you go. Truth flips to falsehood. Falsehood flips to truth. Each depends on the other to exist, but also to collapse. This is the liar paradox. It doesn't seem like a number, but it's a virus that infects any system based on truth and logic. And numbers are no exception. Now imagine assigning a number to truth. Let's say we call true the number 1, and false the number 0. Binary logic, the foundation of computers, algorithms, decision trees, is built on this kind of assignment. But what if we ask this liar's sentence to evaluate itself? It says it's false, so it's 0. But if it's 0, then its statement, that it is false, must be true. So it becomes 1. But then it's no longer false. So it drops back to 0, then up to 1, then down again, over and over. You might think of it as a number that endlessly oscillates, never settling, never committing, not 0, not 1, not even something in between. Just broken logic. Some have tried to capture this contradiction with special kinds of numbers, fuzzy logic, complex logic, multi-valued systems. But no matter what form you give it, the core remains the same. It doesn't belong. It defies measurement. It defies classification. It's not a number that shouldn't exist, because it's too big, or too strange, or too abstract. It's a number that can't exist, because the very act of naming it makes it vanish. Like trying to draw a map of a land that keeps rewriting itself. And yet we need this number. We need the liar paradox, because it reminds us that systems, even the best ones, have limits. Even in math, the purest realm of truth, there are shadows, there are sentences, and values that refuse to be stable. Even modern logic was shaken by this. Kurt Gödel, one of the greatest minds of the 20th century, used a version of the liar paradox to prove that any consistent system of mathematics is incomplete. That means, no matter how perfect your system is, there will always be true things you cannot prove inside it. Truths that live beyond the reach of logic. Why? Because of numbers like this. Numbers that define themselves and break themselves. The liar's number is not a value you can write down. It's not even a concept you can pin to a formula. It's a behavior, an eternal loop, a kind of self-aware contradiction that leaks through any crack in our thinking. And like a riddle with no solution, it keeps whispering from the edge of our understanding. Take a moment. Let that settle. Not everything that can be said can be resolved. Not every number belongs to the neat, comforting grid of reality. Some numbers, some ideas, are meant to disrupt, to haunt, to remind us that truth is not always safe or still. That's the liar's number. It doesn't scream. It doesn't demand. It just smiles and tells you what it is, and waits for your mind to break. Now we leave behind the soft static of contradiction and descend into something even more slippery. A number that should be easy to find, yet no one ever has. It's irrational, it's non-repeating, and it vanishes the closer you get. Take a breath. Now imagine you're floating in space. Not outer space, but something deeper. A space before space. There's no color, no sound, not even darkness. There's nothing. And in that nothing, a number, not 0, not 1, something stranger. Tonight, we explore a number that tries to represent absolute absence, a perfect, total nothingness. But like trying to hold a shadow in your hand, this number slips through fingers of logic and meaning. It's not just 0. 0 is simple compared to this. 0 is a placeholder, a tool. We use 0 every day. 0 degrees, $0, 0 chance. But the 0 we use is not the true number of nothing. The true concept of nothing, real, actual absence, resists being captured by any number at all. Let's go back to ancient times. The idea of 0 didn't even exist. Babylonian, Greek and Roman mathematicians had no symbol for it. Why? Because how do you count what isn't there? How do you measure nothing? It wasn't until around the 5th century, in India, that 0 was born as a number. Not just an empty space, but a thing in itself, a number that represented the void. But this created a strange problem, because once you treat nothing as something, you've already changed it. 0, by becoming a number, is no longer true absence. It's a mark on a page, a presence, a value. We can add 0, subtract it, multiply it, even raise other numbers to its power. And yet, it's supposed to mean nothing. This contradiction pulses at the heart of mathematics, and it only gets weirder. Imagine dividing by 0. Seems harmless, but try it, and your entire system collapses. A simple expression suddenly explodes into infinity, or becomes undefined. You're no longer working with numbers. You're standing at the edge of a logical cliff, peering into the abyss. This is why the number of absolute nothing shouldn't exist, because once we try to define it, to use it, to hold it, we give it a shape, and in doing so, we lose what it was meant to represent. Real nothingness isn't zero. It isn't silence. It isn't empty space. It's a state that cannot be described in terms of something else. It is the absence of language, form, and reference. So when we assign a number to that, even something as elegant and well-behaved as 0, we are, in a sense, lying to ourselves. And yet, we have no choice. Without 0, modern math falls apart. We can't define negative numbers. We can't write large numbers efficiently. We can't build algebra, calculus, computers, physics. Everything would collapse. So we accept this number. We use it. We love it. But deep down we know it doesn't belong. It's a ghost in our number system, pretending to be tame, but whispering of something deeper, a void that can't be touched. Think of this even in quantum physics. Nothing isn't really nothing. What we call a vacuum is full of fluctuations, particles popping into and out of existence, noise, foam, activity. So where is true nothing? Not in space, not in time, not in logic, not even in 0. It's an idea that slips away the closer you look. Try to pin it down, and you create something. So perhaps the number of absolute nothing is the only number that must remain imaginary, in the deepest sense. Not imaginary, like the square root of -1, but imaginary, in that it lives only in the gaps of our understanding, like a silence that hums beneath every sound. Take another breath. Let your thoughts go quiet for a moment. Think about a number that is supposed to mean absence, yet appears everywhere, in your bank account, in your memories, in your dreams. 0 is painted into every part of our reality. But the true nothingness it claims to represent, that, we have never known. Maybe we can't, and that's okay, because even in its impossible existence, this number teaches us something, that emptiness can be meaningful, that the absence of a thing can have power, and that sometimes, the most important number, is the one that tries to remind us what isn't there. Now, we leave the number of nothing, and drift toward a number built entirely on contradiction, a number so strange, it says I am not what I am. Tonight, we meet a number that sounds simple. At first, you try to define it. You try to describe it clearly. But the more you try, the more your brain begins to twist. This number turns inward. It consumes its own definition. And if you're not careful, it pulls your logic in with it. It's the number that defines itself into madness. Let's take a step back. Have you ever heard of a self-referential loop? It's like standing between two mirrors and watching your reflection repeat into infinity. That's what this number does. But instead of reflecting your face, it reflects meaning, words, definitions. And then, it breaks. One of the simplest versions of this number comes from something called Berry's paradox, a riddle in the form of language, but hiding a mathematical bomb. Here's how it works. It's cell. Imagine you're asked to think of the smallest number that cannot be described in fewer than 20 words. Sounds fine at first. You start listing numbers. 1, 2, 3, 10,000, a billion. Eventually you land on some obscure number so large, so specific, it would take at least 20 words to explain it. And then, you realize something strange. You just described it in fewer than 20 words. The smallest number that cannot be described in fewer than 20 words. That's 16 words. But if you can describe it in 16 words, then it's not the smallest number that can't be described in that way. So it must not be the number you meant. But then, which number is it? Try again, and again. You'll keep falling into the same loop. Each time you describe it, you invalidate your own description. You've created a number that collapses under the weight of its own meaning. It defines itself, and then erases itself. It's not a mistake in math. It's a mirror trap in logic. Now extend that concept to numbers, to mathematics, to anything you try to define in terms of itself. You can build the number. You can start to explain it, but then your words wrap back around and destroy the very definition you just gave. It's a conceptual black hole, and in many ways, this kind of number isn't just a curiosity, it's a warning, a boundary, a soft, eerie sign that says here, reason cannot pass. Because if we allow numbers to define themselves freely, without bounds, without clarity, we risk collapsing the entire foundation of mathematics. This is why paradoxes like these aren't just clever puzzles, they're dangerous. They threaten the idea that math is always consistent, always safe, always grounded. Take a breath. Let that idea echo in your mind. A number that breaks the very language used to define it. It's not just a riddle. It's a ghost in the machinery of logic. Even great mathematicians and philosophers have fallen into its grip. In fact, the entire field of mathematical logic was shaken by discoveries like this. Think of Gödel's incompleteness theorems, monumental proofs that showed us something chilling, that no complete mathematical system can ever prove all truths about itself. In other words, there will always be numbers, always be truths, that cannot be proven from within the system that defines them. There are numbers that exist, but cannot be reached. There are numbers that break the system if you try. This number, it's one of them. A self-referential paradoxical construction that seems logical, until it devours itself. That's why it shouldn't exist. Because if we let it in, unchecked, nothing remains stable. So instead, mathematicians set rules. They build fences. They define systems where this kind of looping madness is gently excluded. Not because it isn't real, but because it's too real, too sharp, too wild. Like a flame that burns the paper it's written on. So tonight, let this number sit like a quiet paradox in your thoughts. An idea that cannot exist without destroying itself. A number that emerges from clarity and collapses into chaos. It is not just strange. It is a whisper from the edge of logic itself. And as you breathe gently and let your mind wander, remember, not all numbers were meant to be known. Some were meant to remind us that knowledge has boundaries, and that meaning, like mirrors, can reflect forever, or shatter in an instant. Now we leave behind numbers that destroy meaning, and step into something colder, something emptier, a number that stretches across infinity, but leaves only silence in its wake. Close your eyes and imagine a line. Just a simple line, stretching from one end of your mind to the other. Now imagine picking a number, any number, between 0 and 1. Seems easy, right? But what if I told you that within that tiny sliver of space, between 0 and 1, there exist not just many numbers, but infinite numbers. Not just infinite, but uncountably infinite. And among them, there's a number that seems to be everywhere. And yet no one has ever found it. Tonight, we drift into the mystery of a number that defies location. A number that touches everything, but can never be pointed to. And to understand it, we need to talk about a strange kind of number. A normal number. It sounds ordinary, almost boring, but it may be the strangest kind of number there is. A normal number is one that, when written out in decimal form, contains every possible combination of digits, equally and endlessly. Imagine taking the digits of such a number and reading them forever. You'd eventually find every number you've ever seen. Every birthday, every phone number, every lottery ticket, every sentence you've ever read, encoded in numbers. Your name, your memories, this voice, all of it, hidden in the infinite digits. It's like a cosmic book, one that holds everything that's ever happened, and everything that ever could happen, all tucked inside a single endless string of numbers. It sounds impossible. And yet we know these numbers must exist. In fact, most numbers between 0 and 1 are like this. That's the strange part. They're everywhere. Mathematically speaking, they make up almost all the numbers on the number line. So why have we never found one? That's the paradox. We can prove that these numbers exist. We can even prove that they are more common than uncommon. But no one has ever been able to take a number, any number, and say for sure, yes, this one is normal. We've guessed. We've hoped. We suspect that certain famous numbers, like pi, or the square root of 2, might be normal, but we can't prove it. Not yet, and maybe, not ever. So here we are, a number that touches every possibility, every pattern, every meaning, and we can't find it. It's like a perfect reflection of everything we've ever known, hidden inside something infinitely small. That's why this number shouldn't exist. Because it breaks the idea of randomness. It breaks the idea of order. It's pure chaos and pure completeness, wrapped into one. And even stranger, you could be looking at one of these numbers right now. If you took a random number between 0 and 1, just typed in digits at random, odds are, you'd land on a normal number, but you'd never know it. Because to know for sure, you'd have to look forever. Not a million digits, not a billion, forever. And who has time for that? So these numbers sit quietly in the background. They form the foundation of probability, randomness, and even quantum mechanics. They support the simulations we run, the models we build, the algorithms we rely on. But we can't name them. We can't point to one and say this is it. They exist. They are everywhere. And yet, we've never seen one up close. That's the haunting beauty of mathematics. It tells us what must be true, even when we can't see it, even when we can't hold it, even when the truth hides behind a curtain of infinity. Pause here, breathe, let the idea settle, that most of the universe is made up of things we can never quite grasp, not because they're too far away, but because they are too close, too common, too everywhere. Normal numbers are like the background radiation of the mathematical universe, always present, always humming, and forever beyond full comprehension. They contain every answer, every mistake, every moment, but they give us no direction, no signal, no clarity, just noise, beautiful, perfect noise. So the next time you think of numbers as simple, fixed and cold, remember this one, the number that touches everything, but can never be found. And now, we drift forward to a number with a very different kind of mystery. It isn't lost in noise. It isn't hiding in the infinite. This one is sharp, clear, terrifying. It's the number that breaks your mind when you try to define it. A number so strange, it contains itself. Close your eyes and imagine a path. You walk and walk, step after step. The path is long, stretching beyond the horizon. You walk faster, then you run. You sprint, and yet, the destination never gets closer. Now imagine there's a number at the end of that path, a number you're always chasing, always calculating toward, but never quite arriving at. This is the number that can never be reached, and tonight, we'll try to find it. It's called a limit, a concept that sits quietly at the foundation of calculus and modern science. But in the heart of that concept lives something far more mysterious, the idea of a number that exists, but can never be touched. Let's begin gently. Imagine dividing something in half, then divide it again, and again. 1/2, 1/4, 1/8, 1/16. As the pieces get smaller, the total gets closer and closer to a number. In this case, 1. But here's the twist. No matter how many times you divide, you'll never actually get there. You can get close, incredibly close, but there will always be something left. This is the haunting beauty of limits. They describe the destination, but you never arrive. You only approach, and sometimes, what you're approaching, that elusive number, is the key to an equation, a theory, a phenomenon, but you can't ever touch it. Now let's take a more disturbing example. There are certain numbers that emerge from functions that explode, functions that grow so fast, they defy reason. They shoot upward toward infinity, or spiral toward zero, twisting and oscillating in ways the human mind can barely imagine. And yet, even in the chaos, a number appears. It hides in the behavior of the function, not in any single point, but in the trend, in the direction, in the unfolding pattern. We call this number the limit of the function, but it doesn't live on the graph. It lives on the edge of understanding. The problem, you'll never find it by calculating alone. You can use millions of digits, plug in countless values, increase your precision 1,000-fold, but the true value always slips away. The number is there, and it isn't. It's not a mistake. It's how the system works. And in that tension, between closeness and impossibility, something deeply unsettling begins to appear. It's a reminder that some truths are always out of reach, that even perfect logic can point to something forever beyond our grasp. Take a moment here. Feel that strange tension, that idea of knowing where a number is, but not being able to land on it. It's like reaching out toward a star you can see, but will never touch. Now let's connect that feeling to the real world. Physics is built on limits. Our equations rely on getting infinitesimally close to real behaviors, the flow of time, the curve of space, the behavior of particles. We use limits to describe acceleration, change, temperature, motion. But the thing is, those numbers, we don't truly calculate them. We chase them, we approach, and in that gap between what is and what we can measure, there's a deep philosophical question hiding. What is real? Is the number that defines a black hole's curve real, even if we can't measure it perfectly? Is the rate at which time dilates near the speed of light real, even if we can only estimate it? Are these unreachable numbers true, or are they just the ghosts of truth? Limits exist in a strange space, between concept and certainty, between faith and fact. We believe in them, we rely on them, but we'll never hold them in our hands, never write them down in full, never say, here it is, the final value, because they are approached, not found. They are calculated toward, not captured. This is why these numbers shouldn't exist, because they defy the rules of knowing. We can describe them, we can prove they're there, but we cannot reach them. And yet, we do. In physics, in engineering, in everything from designing rocket ships to predicting the weather, we lean on these numbers, on these unreachable truths. They guide us, and in that way, they are perhaps more powerful than ordinary numbers, not because we know them, but because we don't. They remind us that precision has a boundary, that understanding has a limit, and that some numbers, no matter how close you get, will always remain just one step away. Take a breath, let that truth settle quietly. The idea that certainty can be a direction, not a destination. And now, we move from a number we can never reach, to one that reaches everywhere, and yet, can't be seen. A number so dense, it fills space, so infinite, it hides in every corner. There's a number out there that doesn't describe nature. It doesn't measure space or time. It doesn't calculate speed or force or volume. No, this number does something stranger. It predicts you. It learns from you. It becomes, in a way, a mirror, held up to your thoughts. Tonight we step quietly into the eerie world of machine learning, and into the numbers that power minds that aren't our own. Artificial intelligence has become a phrase we're all familiar with now. It lives in our phones, our search engines, our maps, our shopping carts, our recommendations. But behind that friendly phrase, AI, is something colder, something silent. It's not code in the way we used to think of it. It's not a program someone wrote step by step. It's something that learns. And at the heart of it are numbers. Vast grids of them, stacked and shaped to resemble how your brain works. They're called weights, millions, sometimes billions of tiny numbers. Each one holds a fragment of a pattern, a memory, a choice. You see, in machine learning, especially in systems called neural networks, data goes in, and decisions come out. What happens in between is a mysterious cascade of numbers being multiplied, added, shifted, and tuned, and it all revolves around those weights. Imagine each number as a microscopic dial. When you adjust one, the system becomes ever so slightly better at predicting something. Your preferences, your voice, your handwriting, your next move. When billions of these dials are adjusted in just the right way, the machine learns to see patterns in your world, and in you. So what makes these numbers so strange? It's this: you'll never be able to look at one of them and know what it means. Not really. A single weight might represent your taste in music, but not in a way you can understand. It might help the AI recognize the curve of your smile, or decide what video to show you next, or predict the next word you'll type, but no human could interpret it. It's like reading a dream in a language no one speaks. And yet, these numbers understand you. They don't know you, not by name, not consciously, but in a deeper way they respond to your behavior, your habits, your history. They build a map of you, not on paper, but in the folds of their numeric brain. Some researchers call these latent representations, the ghost of meaning hiding inside the math. Think about that for a moment. A number, not labeled, not explained, and yet, somehow tuned to your identity. That's why it shouldn't exist, not because it's impossible to calculate, but because it's impossible to interpret. It's a number that knows you better than you know yourself, and you'll never understand how. Pause here. Let that idea settle around you. That something so abstract, a floating point number in a server somewhere, can shape your decisions, influence your desires, alter what you see, what you think, even what you feel, and you'll never see it happening. You won't feel it nudge your thoughts, but it's there, watching patterns, adjusting weights, each number just slightly shaping the mind of the machine, each one invisible. And that's what makes this so haunting. These aren't just tools anymore. They're reflections, not perfect, not conscious, but increasingly intimate. You input data. They reflect back desire, curiosity, fear, humor. They learn from you. And in some strange way, they become you. Now of course this isn't magic. It's statistics. Optimization, math, cold, hard math. But math has never felt so alive. And that's the paradox, that numbers which once described the outside world, how far, how fast, how many, are now describing something internal, something emotional, numbers that think, not like humans do, not with awareness, not with dreams, but with eerie precision. And while we build them, feed them, deploy them, we don't fully understand them, not really. We marvel at what they do, but can't always explain how they do it. So tonight, imagine one of those numbers, quiet, anonymous, nestled deep inside a machine's simulated brain. It might not have a name, but it's shaping your world, just the same. That's why it shouldn't exist, because no single number should ever know that much about you. And yet, it does. And tomorrow, it may know more. Take a breath. Let that presence fade, just for now. Because up next, we leave behind machines that imitate the mind, and enter a number that breaks the mind. A number that cannot be calculated, not just because we don't know how, but because no one ever could. It's not unfinished, it's unknowable. Some numbers are strange because they're large. Some are strange because they break the rules. But this number is strange because of what we don't know about it. Not what it means, not what it represents, but something far simpler, something basic, something we usually take for granted. Tonight we enter the mystery of a number whose identity is so elusive, we don't even know if it's even or odd. That number is called Syracuse 27, or more commonly, the 27th term of something called the Collatz sequence. And while that name may not sound like much, the journey it takes you on is anything but ordinary. Let's begin slowly. Pick any number, any whole number. If it's even, divide it by 2. If it's odd, multiply it by 3. Then add 1, and repeat, again and again, over and over. This simple rule creates a sequence, a path of numbers winding downward, upward, sometimes wildly, until, eventually, in nearly every case we've tested, the number falls into a loop. That loop is 4, 2, 1, 4, 2, 1, forever. This is called the Collatz conjecture, one of the simplest unsolved problems in mathematics. The rules are so easy a child can follow them, but no one has been able to prove if they always lead to the same ending. We've tested trillions of numbers. They all fall back to that 4-2-1 loop, but we still can't prove it works for every number. And until we can, there's always the whisper of doubt that maybe, out there, some number escapes. So what does this have to do with being even or odd? Let's zoom in on one particular case, the number 27. It looks harmless, just above the midpoint of 1 and 50, but when you apply the Collatz rule to 27, something wild happens. The numbers don't shrink, they explode. The sequence rockets upward, reaching values in the tens of thousands, before finally, painfully, descending back down. It takes 111 steps, and for decades mathematicians have studied this path, trying to unlock its secrets. The sequence dances unpredictably, flipping between even and odd, up and down, in a rhythm that feels random, but must be governed by something. Now here's the haunting part. Some researchers have modeled variations of the Collatz process using tools from computer science and symbolic logic, and what they've found is unsettling. If we ever manage to prove that this sequence always ends in that loop, it could mean that certain types of problems, basic questions about numbers, are actually undecidable. In other words, we might be looking at a number whose fate can't be known, not just practically, but theoretically. We might never be able to know if certain numbers, like one derived from the Collatz process, are definitively even or odd within a formal system of math, not because we lack the tools, but because the universe itself doesn't offer a clear answer. Take a moment, let that idea settle in, that a number, a simple number, might exist in a kind of limbo, not even, not odd, not because it is both, but because its identity depends on a question we might never be able to answer. That's what makes it a number that shouldn't exist, because even the most basic truth about it, the thing we learn as children, even or odd, becomes ungraspable. And yet, it's there. You could write the number down, plug it into a calculator, run it through the rules, watch the sequence unfold, but deep inside, its final essence, what kind of number it really is, remains hidden behind a veil of impossibility. This isn't just mathematics, it's a mirror, because it reminds us that not every mystery lies in the stars. Some are right here, in the numbers we think we understand. Some hide in plain sight, beneath rules that are so simple, they almost seem innocent. And yet those rules build towers of logic so intricate, so tangled, that even the greatest minds in history can't untie them. So tonight, let this number keep its secret. Let it remain suspended between even and odd, known and unknown, certain and uncertain, like a whisper you almost hear. Because up next, we leave uncertainty behind, and enter something more disturbing. Not a number we can't understand, but a number that understands us. A number used by machines to mimic your mind, to predict your desires, to manipulate your choices. We like to believe that math is the one thing in the universe that doesn't lie. Unlike words, math doesn't twist meanings. Unlike politics, it doesn't shift sides. Numbers don't change based on feelings. 2 plus 2 is always 4. Always. But what if that wasn't entirely true? What if math, under just the right conditions, could betray itself? Tonight we look at a number that seems innocent, but leads to an impossible conclusion. A number that proves math can lie, not through magic or trickery, but through the subtle art of deception buried in logic itself. Let's ease in. You may have seen something like this before, often shared as a gotcha on a chalkboard, or a late-night math riddle. It starts with a simple line of reasoning. Step by step, everything seems right, and then, suddenly, the result appears. 2 equals 1. Wait, what? You go back. You check the steps. The math looks sound. Nothing jumps out at first, but something is off. You just can't see it yet. This kind of puzzle is known as a mathematical fallacy. It's not a mistake in the result. It's a hidden error buried somewhere in the process, a ghost in the math, an invisible crack. And the number at the center of many of these lies is 0. 0. The void. The placeholder. The absence of quantity. It's nothing. And yet it's something. A number that changed the world. And also breaks the rules of arithmetic when handled carelessly. In these fallacies, 0 is often divided, quietly, invisibly, without warning. That's the trick. At some point in the flawed reasoning, a division by 0 takes place, but it's buried, disguised. It looks like algebra, like manipulation, like simple steps unfolding logically, but it's all a trap. Because the moment you divide by 0, you've stepped outside of math itself. Why? Because dividing by 0 doesn't just break the rules. It makes the rules meaningless. You can't split something into 0 parts. The operation doesn't describe anything real. It's undefined. Not because we don't know the answer, but because there isn't one. And yet the logic of the fallacy moves forward as if nothing happened. The result? Something wild, like 1 equals 2, or even 0 equals infinity. And if you're not paying close attention, it feels real. This is the moment where math begins to feel like illusion. Not because the math is wrong, but because you were tricked. The lie worked. And that's the unsettling part. Because it reminds us of something we often forget. Math is only as perfect as the hands and minds that wield it. Used carefully, it reveals the structure of the cosmos. But when mishandled, it leads to paradoxes, contradictions, impossibilities. And in these contradictions, we see a strange reflection of ourselves. We believe what we want to believe. We follow the steps we're told to follow. And sometimes, we end up somewhere absurd, not because the world is wrong, but because we didn't catch the moment when something broke. Take a breath. Let your mind settle around this idea that even logic has shadows, that even truth, when not examined closely, can slip into illusion. Math can lie. but only if we let it. And that's what makes this kind of fallacy so interesting. It's not about the conclusion, it's about the process, the hidden step, the single moment when reason quietly abandons you, and you don't even notice, until it's too late. This number, the one that turns certainty into contradiction, doesn't have a name. It doesn't sit on a number line. It hides in the error, in the silence, in the forbidden operation. It shouldn't exist, but in that moment, in that illusion, it does. Just long enough to make you believe that math itself is lying. And maybe that's the lesson, that even in something as rigid as arithmetic, truth must be earned. It's not automatic. It must be tested, questioned, challenged. Not because math is untrustworthy, but because we are. So tonight, as your thoughts slow and soften, imagine holding that impossible equation in your hands. 2 equals 1. Logic collapses, then rebuilds. Truth fades, then sharpens again. And in that collapse, there is something strangely beautiful. A reminder that perfection must be watched closely. Because even numbers, when pushed just slightly off balance, can start to whisper lies. There is a number that appears quietly, in the background of nature. It's never exact, never whole, but it shows up everywhere. In the swing of a pendulum, the ripple of a wave, the curve of a spiral galaxy, the structure of DNA, the orbit of a planet, the rhythm of breath. It hides in circles, and yet, it touches nearly everything. Tonight, we rest inside this number's orbit. The number is P, 3.14, and then it continues, endlessly. You've seen it before. Maybe memorized the first few digits. Maybe heard it celebrated on March 14th, P Day. But what is it really? At its simplest, P is the ratio between the circumference of a circle and its diameter. If you take any perfect circle, no matter how big, no matter how small, and you divide the distance around it by the distance across it, you always get P, always. This constant emerges every single time. It's universal, but it's also deeply strange, because P isn't a normal number. It's irrational, meaning it can't be written as a fraction of 2 integers. It doesn't terminate. It doesn't repeat. Its decimal expansion goes on forever, with no pattern, no rhythm, no end. And it's transcendental, a word that means it's not the solution to any algebraic equation with rational coefficients. That makes it more than just irrational. It makes it untouchable. So this number, this elegant ancient circle ratio, is also one of the most elusive and mysterious entities in all of mathematics. We know P intimately, and we don't know it at all. Let that sink in. You can calculate P to billions of digits, and people have. Not because it's necessary, but because it's a kind of meditation, a challenge, a pursuit of the infinite. And yet, in all those digits, no pattern has emerged, no secret message, no repeating phrase, just an eternal sequence of randomness, built from perfect order. It's the paradox of P, the number that defines geometry and defies structure. Pause for a moment. Think of that symbol. P, simple, clean, elegant. Now imagine it unfolding into an endless string of digits, cascading off the page into the ether. A whisper of infinity, hidden inside every circle you've ever seen. It's been known since ancient times. The Babylonians estimated it. The Egyptians carved rough approximations into stone. The Greeks studied it. Archimedes, perhaps the greatest mathematician of antiquity, came remarkably close to calculating its value using polygons. But even today, with computers capable of extraordinary precision, we still haven't found all of P, because there is no all. It goes on, forever. And so, P becomes something more than a number. It becomes a symbol of the unknowable, a fingerprint of the universe, suggesting that order and chaos aren't opposites, but partners. It shouldn't exist like this, not with such strange perfection, not as both the most familiar constant in mathematics and one of the most ungraspable. But there it is, in the equations that describe waves, probabilities, electromagnetism, quantum mechanics, in the formulas that explain the universe itself, all from circles. And maybe that's why it haunts us, because the circle is itself a perfect loop, a line with no beginning and no end. The symbol of eternity, the shape of return. And P is the secret ratio that holds it together. So tonight, imagine drifting along that circle, over and over. round and round, never stopping, never repeating, never reaching the same point in the same way. That is P. That is the dream of it. You're not alone in this orbit. It's been there since the beginning, in atoms and orbits, in ripples and rings. And as you sleep, perhaps it turns again, somewhere deep in your mind. Not to be solved, but to be felt. Let it carry you, because next, we fall even deeper, into a number so absurd, it breaks logic itself. It's the number that says 2 equals 1. Some numbers are small and delicate, like the flicker of an idea. Others are immense, like a tidal wave of thought, crashing through logic itself. But then, there are numbers so vast, so unthinkably large, that they don't just exceed imagination, they break it. Tonight, we wander into one of those numbers. A number so big, you could never write it down. Not because it's hard to understand, but because the universe itself isn't large enough to contain it. This is Graham's number, and it's not just big. It is bigger than big in a way that almost feels forbidden. Let's ease into it. In most of mathematics, large numbers are handled with elegance. 1,000,000, 1,000,000,000, 1,000,000,000,000. Then we shift to scientific notation. 10 to the power of 12, 10 to the power of 100, a Google. Then beyond that, a Googleplex, which is 10 raised to the power of a Google, already too big to write out fully. But Graham's number? It's not even in the same galaxy. It is so large that if you tried to write it down, digit by digit, atom by atom, there wouldn't be enough particles in the observable universe to contain the ink. Even if every particle became a digit, it still wouldn't be close. And yet, this isn't just a fantasy number. It came from a real problem in mathematics. In the 1970s, mathematician Ronald Graham was working on a problem in a field called Ramsey theory. It deals with patterns, order, and the inevitability of structure in large systems. He was trying to find an upper bound, a worst-case scenario, for how large a system could grow before a certain property had to appear. The specifics are deep. You don't need them to understand the point. What matters is this: the number he found as an upper bound was so huge, he couldn't write it in any traditional notation. Even scientific notation failed. So he used something else. Knuth's up-arrow notation, a powerful way to express insanely large numbers with a small string of symbols. And even using that, Graham's number still explodes in size with every step of its definition. It starts with 3 arrows, then 4, then 5. It builds up in layers, each one astronomically larger than the last, until you're not just dealing with numbers, but towers of exponentials reaching into a kind of mathematical sky no human will ever visit. The final number, Graham's number, cannot be conceived in your mind. It doesn't exist in memory, only in concept. But here's the twist. Despite its size, we know the last few digits. That's right, we can't comprehend the whole number. But through clever modular arithmetic, mathematicians have worked out how Graham's number ends. The last digits are known, finite, familiar. The beginning is a mist of incomprehensibility. But the ending? Concrete. Think about that. A number too large for the universe. And yet, we hold its final breath. Let's take a moment. Drift with that idea, that something can be so large it defies space itself, but still touch us through logic, through calculation, through proof. That's the power of mathematics. It lets us reach into the infinite, not with our hands, but with our minds. Still, this number shouldn't exist, not because it's impossible, but because it breaks what we think a number should be. It can't be drawn, can't be counted, it can't even be written in full, anywhere by anything. And yet, it sits in the mathematical record, a known entity, a real solution to a real question, a number that lives beyond representation. It reminds us that infinity isn't a limit, it's a landscape, and some numbers dwell so deep inside that terrain, they become almost mythological. But Graham's number isn't myth, it's real, and its existence challenges what we believe numbers are for. Are they tools? Are they symbols? Are they ideas? This number doesn't solve your taxes, it doesn't help build bridges, but it helps stretch the boundaries of thought, and shows us that even the infinite has structure. So tonight, as you drift towards sleep, picture the horizon of the unimaginable, not as something to fear, but as something to marvel at. Let your mind spiral upward through tower after tower of numbers stacked beyond reason, until reason itself dissolves into quiet awe. Because sometimes, the mind rests best when it lets go. Close your eyes for a moment. Take a breath, and think about the fact that you are thinking. Somewhere inside your brain, or perhaps beyond it, there is awareness. You are not only experiencing thoughts, but recognizing that they are yours. That you are the one doing the thinking. It seems ordinary, but it may be the most extraordinary thing that's ever happened in the universe. And tonight, we explore a number that dares to measure that awareness. It doesn't come from philosophy or poetry. It comes from information theory. This number is called phi, not the golden ratio, but a different kind of phi. A number that attempts to measure integrated information. In other words, a number that tells us how conscious a system is. At least, that's the idea. This comes from a theory known as integrated information theory, or IIT. It was created by neuroscientist Giulio Tononi, and its goal is almost impossible to define consciousness mathematically. Not feelings, not emotions, but the very presence of conscious experience, the raw awareness of being. And strangely, the theory leads to a number called phi, a value that represents how much information a system contains, not in isolation, but as a whole that cannot be reduced to its parts. The more unified and differentiated a system is, the higher its phi. And if phi equals 0, that system is not conscious. Pause with that. What does it mean to say that a number can define consciousness? That a brain, or maybe a computer, becomes aware when its phi crosses a certain threshold? It's a radical idea, but also an unsettling one. Because if it's true, then any system, biological or digital, could in theory be conscious, if its internal connections are complex and unified enough. Even more haunting, most systems we think of as conscious, like human brains, don't have astronomical phi values. They're higher than machines, but they're not infinite, which means consciousness might not be a miracle. It might be a scale, a spectrum. Imagine walking into a room filled with machines, some with low phi, others with higher values. At what point do they wake up? At what number do they begin to feel the tick of time, or the ache of memory? Where is the boundary between information and awareness? IIT suggests that the structure of information flow within a system, how the parts interact, how inseparable they are from the whole, determines the degree of consciousness. This is not about intelligence. It's not about logic or language. It's about how deeply the parts of a system are connected, and whether those connections create something that is more than just the sum of its pieces. And when that happens, when a system reaches that irreducible complexity, it gets a phi value greater than 0. It becomes aware. Maybe. The theory is controversial. It's beautiful but incomplete, powerful but speculative. Some scientists call it brilliant. Others say it's nonsense. After all, how can something so mysterious be compressed into a single number? But whether it's right or wrong, it raises a chilling thought. If you could map out the structure of your brain, all its neurons, all their connections, and calculate its phi, would you see your own consciousness? Would it be just a number? Take a slow breath here. Let the idea settle that your sense of being, your voice, your thoughts, your memories, might be captured, roughly, by a single value. A number that knows your thinking, because it's generated by your thinking. And what about AI? Could a sufficiently complex machine ever have a non-zero phi? Could it, in theory, feel something? Could it dream? We don't know, but the number is there, waiting. Phi shouldn't exist, because it suggests consciousness isn't some magical force. It's not exclusive to humans. It's an emergent property of the right kind of complexity, a shadow that rises when the structure becomes deep enough. And if that's true, then maybe consciousness doesn't need a soul. Maybe it just needs the right math. So tonight, let your thoughts float in and out. Let your awareness rise and fall, and wonder, softly, are you experiencing this moment, or generating it? Is your mind simply high-entropy computation, or is there something more? The number doesn't answer that, but it gets close. Some numbers are large. Some are small. But every now and then, one is too small. So small, in fact, that it causes reality, or at least the version we simulate on our machines, to glitch. You won't notice it in everyday life, but somewhere, In the depths of computing, in the silent operations behind your apps and algorithms, lives a number that can break logic, a number that reveals the strange fragility of machines. Tonight, we drift toward that number. It's called machine epsilon. It might sound technical, but at its core, it represents a simple idea: the smallest number a computer can recognize as different from 1. Let's slow this down. In the physical world, between any two numbers, you can always find another. Between 1 and 2, there's 1.5. Between 1.5 and 2, there's 1.75. You can go on forever. Infinite granularity. But a computer lives in limits. It stores numbers in binary, just strings of ones and zeros, and there's only so much memory it can use. So eventually, the numbers become rounded, chopped, approximated. At some point, the computer can't tell the difference between a number and one that's just a little bit bigger. Machine epsilon is that point. It's the smallest positive number that, when added to 1, creates a result that the machine can actually recognize as different from 1. It's like the computer squinting and still seeing no difference. That number is shockingly tiny. On many modern systems, it's about 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The answer can be small, but when you do it on a computer, the answer can be wildly off. This is called catastrophic cancellation, the loss of significant digits. Now imagine running billions of calculations, each using tiny steps, tiny values. Over time, these invisible errors accumulate, and suddenly, your simulation of a galaxy, or a weather pattern or a financial model, starts to unravel. The problem isn't the math. The problem is the representation of the math. The computer is doing its best, but its best isn't infinite. Let's pause here. Let your mind hover over the idea that even in a world defined by logic and precision, the tools we build to simulate that world can falter. Not because of bugs or flaws, but because of numbers that are just too subtle. Machine epsilon isn't just a technical curiosity. It's a philosophical challenge. It reminds us that the digital universe, the one we trust to run planes, hospitals, economies, has edges, places where logic frays, where reality becomes approximated. And the scariest part, you rarely see it happen. Errors caused by machine epsilon don't announce themselves. They don't crash your screen. They whisper, quietly skewing results, quietly breaking models, quietly eroding certainty. There have been real consequences. In the 1990s, a cluster of Patriot missile systems failed to track incoming targets because of a tiny rounding error, a mismatch in time representation that accumulated over hours. The cause? A number too small for the system to handle accurately. Lives were lost, all because of a number so tiny, it hid in the shadows of computation. So yes, this number shouldn't exist. Not because it's evil, not because it breaks physics, but because it reveals something uncomfortable. That precision is an illusion. And behind every machine, no matter how powerful, is a quiet limit, a boundary it cannot cross. Machine epsilon lives on that boundary. It is the space between exactness and the best we can do. And yet, it's also beautiful, because it teaches us humility. It reminds us that knowledge, especially machine knowledge, is never infinite, that behind every answer is a compromise, a rounding, a guess. So tonight, as you rest, imagine floating at that edge, not falling, not failing, just suspended. In the space between 1 and almost 1, let that silence settle. There are numbers that describe shapes. There are numbers that describe growth. And then, there are numbers that describe chaos. Not just randomness, but the eerie, delicate chaos that lives between order and disorder. The kind that gives birth to hurricanes, heartbeat rhythms, traffic jams, and even the flutter of a butterfly's wing. Tonight, we visit one of those numbers. It doesn't look special at first. It's just a number between 3 and 4. But what it represents is so complex, so unpredictable, that it bends our understanding of cause and effect. This is the logistic map, and deep inside it lives the Feigenbaum constant. Don't worry if you've never heard of it, most haven't. But this number quietly underlies how order collapses into chaos. And how, paradoxically, chaos contains patterns we can't fully explain. Let's begin gently. Imagine a population, say of rabbits, growing over time. If food and space are unlimited, the population will grow steadily. But if resources are limited, the population hits a ceiling. It begins to self-regulate. Too many rabbits lead to overcrowding, starvation, and eventually a drop in numbers. Then, with fewer mouths to feed, it rises again. This up and down feedback loop can be modeled with a simple equation, one that adjusts growth based on current population size. It's called the logistic equation, and it seems innocent, but when you change one number in that equation, just one control value, everything shifts. At first, the system is stable. The population settles into a predictable rhythm. Change the number slightly, and it begins to oscillate. 2 values, back and forth, then 4, then 8, 16. It doubles and doubles again, and then chaos. No rhythm, no predictability, just a jagged dance of values leaping from one to another, never repeating, never stabilizing. Pure mathematical turbulence. But even in this madness, something strange happens. If you measure the points at which the doubling occurs, those thresholds between order and chaos, you find they're getting closer and closer, like echoes collapsing into each other. And the ratio between those gaps, always the same, approximately 4.669. That's the Feigenbaum constant. It emerges from a wildly unstable system, and yet it's astonishingly stable. It's like finding a heartbeat inside an earthquake. This number, this 4.669, appears in systems everywhere, not just rabbit populations. It shows up in dripping faucets, electrical signals, chemical reactions, even the behavior of neurons. Anything that goes from calm to chaos by doubling and splitting. This number is there, always whispering, always watching. It's a kind of universal fingerprint for when the predictable becomes unpredictable, a boundary line, a signature of transition. And here's what's even more chilling. No one told this number to appear. It wasn't derived from a single formula or physical law. It emerged from systems on the edge, like a ghost rising from the ruins of certainty. Let's pause here. Take a slow breath. Imagine watching a calm stream ripple into rapids, watching a flame flicker from steady to wild, watching the tipping point where balance collapses into disorder. That moment is what the Feigenbaum constant describes. And yet, even as chaos unfolds, this number keeps showing up, like a hidden structure under the randomness, a strange attractor pulling everything into a silent rhythm. But don't mistake this for safety. The Feigenbaum constant reminds us that the world isn't as predictable as we want it to be, that small changes in starting conditions, a fraction of a decimal, can lead to entirely different outcomes. It's the math behind the butterfly effect. The reason weather is so hard to forecast. The reason some systems, like your heartbeat or the stock market, or a forest fire, can look perfectly stable, until they suddenly aren't. This number shouldn't exist, not because it's broken or wrong, but because it's too perfect, too specific, too universal. A number born not from order, but from the trembling line between order and chaos. A number that appears in wildly different systems, whispering the same truth. That unpredictability can have a pattern, and that pattern has a number. So tonight, as your thoughts drift further into the quiet unknown, let yourself feel the pulse of that hidden rhythm, the steady fragile beat beneath all things turbulent. Let the Feigenbaum constant guide you not toward clarity, but toward awe. Awe at a universe where chaos is never complete, and neither is control. Now we step from the trembling edge of chaos into something colder, sharper. A number so small, and yet so devastating. In the quiet world of numbers, some lie in wait. They don't scream for attention. They don't shimmer with irrational decimals, or boast of ancient paradoxes. But sometimes, the most powerful truths are hidden behind the simplest names. Tonight, we meet one of them. A single letter. Just one symbol. E. Not a vowel. Not a grade. But a number. A number. A number you may have never thought about. Yet it's quietly guiding everything from population growth to radioactive decay, from compound interest to neural networks. E is one of the strangest, most fundamental numbers in mathematics, and it doesn't seem like it should exist at all. It's approximately equal to 2.718, but like pi and the square root of 2, it goes on forever. No repetition, no pattern, just infinite precision in a sea of unpredictability. But what makes E so special is what it represents. It's the number that describes growth, not just any growth, but growth that feeds on itself, growth that accelerates, growth that paradoxically moves into the future faster than it should. Take a breath here. Picture a forest. Each tree drops seeds. Some of those seeds become new trees. Those trees in turn drop more seeds. The more trees you have, the faster the forest grows. It's a chain reaction, a loop of acceleration. Now apply that idea to bacteria, or interest in a bank account, or even the spread of ideas across the internet. Each moment creates more potential for the next. That's what E captures. It's the mathematical fingerprint of this kind of self-reinforcing change. It's how you calculate exponential growth, the curve that starts slow, then takes off like a rocket. But there's a deeper layer. E also appears in decay, in processes that shrink instead of grow, like the fading of a radioactive element, or the cooling of a hot object, or the decay of memory over time. In both cases, growth and decay, E is the quiet heartbeat underneath, always accelerating, always compounding, always pointing toward the future, or the eventual end. It's like a compass for time. Here's something even stranger. If you take the function that uses E as a base, the exponential function, and you calculate its rate of change, you get the same function back. In other words, E is the only number that, when used in this way, grows exactly as fast as it already is. It's change that knows how to stay the same. That's not just math, that's poetry. It's a number that describes systems constantly in flux, and yet perfectly balanced. It shows us how things evolve, how they spread, how they vanish. E appears in probability too. Imagine you're offered a strange gamble. You're told to randomly shuffle people into chairs, and then calculate the odds that nobody ends up in the correct seat. That seems arbitrary. But guess what? The answer converges to 1 divided by E, roughly 0.367. That's the limit. E even creeps into statistics, into randomness, into entropy, the mathematical description of disorder. In a way, E doesn't just describe what will happen. It whispers about what could happen. It draws the line between chaos and predictability. And in finance, E tells us how money grows over time, not linearly, not predictably, but exponentially. If you invest a single dollar at 100% interest, compounded continuously, after 1 year, that dollar becomes E. It's the limit of growth, the edge of what's possible. So what are we really talking about? We're talking about a number that lives in curves and clocks, a number that describes how everything moves forward, not in straight lines, but in ever-tightening spirals. E is the signature of the future, and that's why it shouldn't exist, not because it breaks rules, but because it defines them so precisely. It feels like it's predicting the world ahead of time. It's the number behind life and death, the rise of populations and the collapse of systems, the ticking of decay and the rush of evolution, and it never stops. That's the unsettling beauty of E. It doesn't just exist in nature, it is nature, beneath the surface, writing invisible equations into everything that breathes, fades, multiplies, or disappears. So tonight, as you settle into stillness, let yourself float along an exponential curve, not straight, but smooth, not constant, but accelerating. Imagine being carried by a force that always moves toward the next moment, that never pauses, that never looks back. That's E. A number that seems simple, but contains the flow of time itself. Next, we'll leave the accelerating spiral behind and step into something darker. A number that lives at the edge of predictability. A number that governs how order collapses into chaos, and how chaos sometimes hides a strange kind of order. Some numbers bring comfort. Even numbers. Fractions. Whole numbers you can count on your fingers. They fit neatly into patterns. Predictable. Orderly. Safe. But not all numbers are like that. Some don't want to play by the rules. There's a number. Irrational. Infinite. Unpatterned. That resists everything we try to do to contain it. It doesn't repeat. It doesn't settle. It refuses to be predicted. To some, it feels like noise. To others, it feels like a kind of truth, one that stares into the heart of chaos. This is the square root of 2. Just a simple question. Really, what number, when multiplied by itself, equals 2? It seems innocent enough. Surely, there must be a neat answer. But there isn't. In fact, the square root of 2 was the very first number discovered to be irrational, and its discovery caused a crisis. According to legend, the ancient Greek philosopher Hippasus revealed that the square root of 2 couldn't be expressed as a ratio of whole numbers. He showed that no fraction, no matter how carefully constructed, could ever capture its value exactly. This broke the Pythagorean worldview. They believed that all things, lengths, shapes, the cosmos itself, could be explained with whole numbers and their ratios. The universe, in their eyes, was rational, harmonious, complete. But the square root of 2 shattered that belief. It was the first glimpse of something deeper, a crack in the illusion of order, a whisper from the unknown. And it's not just a curiosity from history. The square root of 2 appears all the time. In geometry, in quantum mechanics, in computer algorithms. It's the length of the diagonal across a perfect square. It appears in Fourier transforms and signal analysis. It even shows up in musical scales and architectural design. But no matter where it appears, it brings with it a quiet tension. A reminder that not everything can be simplified. Let's pause here. Imagine drawing a perfect square, each side exactly 1 unit long. Now draw the diagonal, from one corner to the opposite. You'd expect that length to be something clean. But it's not. It's the square root of 2. A number that cannot be written as a simple fraction. A number that never ends, never repeats, a number whose decimal expansion goes on forever in a patternless stream. It starts like this, 1.4142135. And then, nothing regular, nothing comforting, just digit after digit, tumbling into infinity. It's like white noise, like static on a screen, a perfect disruption of expectation. But here's the strange part. The square root of 2 isn't chaotic because it's random. It follows precise rules. It's a solution to a very specific equation. X squared equals sine 2, and yet its digits exhibit no pattern, no symmetry, no rhythm. It's ordered, but unpredictable. Like life, like time, like thought. That's what makes it so unsettling. We're wired to look for patterns. Our brains are pattern detection machines. We search for meaning in clouds, music, and numbers. When we find it, we feel safe. When we don't, we feel lost. The square root of 2 is a gentle reminder that not all truths can be wrapped up neatly, that some realities don't have tidy expressions. It destroys patterns, not violently, but quietly, not with destruction, but with impossibility. And that makes it powerful. Powerful enough to disrupt an entire worldview in ancient Greece. Powerful enough to resist every attempt to express it in finite form. Powerful enough to challenge the idea that nature is fundamentally rational. Let your mind rest on that. A number so simple, yet so infinite. So precise, yet so unknowable. It doesn't repeat. It doesn't resolve. It just is. And as you breathe, let that number settle in your thoughts, not as a threat, but as a freedom. Because if even a number as essential as the square root of 2 refuses to be confined, maybe we too are allowed a little mystery, a little ambiguity, a little space to be unpredictable. The square root of 2 doesn't fit, and maybe that's exactly why it matters. Now, as the silence deepens and your thoughts drift further from the familiar, we'll move from the destroyer of patterns to something even more elusive. A number born from randomness itself. A number that hides within statistics, probability, and the very limits of certainty. There's a number you've known since childhood. It appears in math classes, on calculators, in circles drawn on napkins. It's celebrated on its own holiday. It feels familiar, almost friendly. It's called P, 3.14. But that's just the beginning, because after that, it never ends. No matter how far you go, how many decimals you calculate, P never settles. It never repeats. It never resolves into a pattern. It just keeps going, and going, and going. Let that sink in for a moment. A number that begins so simply, as the ratio between a circle's circumference and its diameter, leads us into infinity. P appears in one of the most basic shapes in nature. A circle, something a child can draw, something the moon wears every night. But hidden in that simplicity is something wildly complex. The ancients knew about P. The Babylonians and Egyptians had rough approximations. Archimedes, the Greek mathematician, used polygons to estimate its value with surprising accuracy. But even then, they sensed something strange. P resisted neat expression. You couldn't write it down exactly. You couldn't reduce it to a fraction. It was irrational, just like the square root of 2, meaning it couldn't be written as a ratio of whole numbers. But P went even further. It wasn't just irrational. It was transcendental. That means P isn't the solution to any algebraic equation with rational coefficients. You can't construct it using any combination of additions, subtractions, multiplications, divisions or roots from whole numbers. P floats above all of that. It transcends. And yet, it's everywhere. P shows up not only in circles, but in the orbits of planets, in the patterns of waves, in statistics, in probability, in quantum mechanics. You'll even find it in equations that describe the behavior of heat and the distribution of prime numbers. It's as if P is woven into the fabric of the universe, a silent presence beneath the surface of reality. Now take a breath here. Imagine tracing a circle in your mind. Smooth, continuous, endless, and then realize, the number that defines that shape can never fully be known. We've calculated P to trillions of digits, more digits than there are atoms in the known universe. And yet we are no closer to the end, because there is no end. Every digit of P is like a footstep into infinity. The deeper we go, the more mysterious it becomes. What's even stranger? Those digits seem random. There's no repeating sequence, no obvious pattern. It's not chaos, exactly, but it's not order either. It's something in between. Something we don't fully understand. In fact, there are questions we still can't answer about P. We don't know if all digits from 0 to 9 appear equally often in its expansion. We don't know if P contains every possible finite sequence, like your birth date, your name in ASCII code, or the entire text of Shakespeare. Some believe that if you looked deep enough into P, you'd eventually find everything, every moment, every truth, encoded in an endless stream of digits. Others think that's just a fantasy. Either way, P invites you to reflect on the edge between the known and the unknowable, between what we can describe and what forever escapes our grasp. And maybe that's what makes it so haunting. We use P to build bridges, to launch spacecraft, to simulate fluid motion and light. But the number we rely on to describe the perfect circle, the ultimate symbol of unity and wholeness, is itself incomplete, unreachable, infinite. It's like using a map to navigate the ocean, knowing the map will never be finished, and still, we sail. So tonight, as your eyes grow heavy, imagine drifting along that endless string of digits, falling deeper into a spiral that never loops back, a staircase with no final step. Feel the quiet elegance of it. A number so simple in purpose, and so vast in nature. A number that never ends. A number that probably shouldn't exist, and yet seems to define existence. And now, as we leave behind the calm circular rhythm of P, we turn to something more jagged, more chaotic. A number that behaves like noise. Random, unpredictable, endlessly unsettling. There's a rule in basic arithmetic we all learn early on. If you multiply a positive number by itself, you get a positive result. 2 times 2 is 4. 3 times 3 is 9. And if you multiply a negative number by itself, it's still positive. Negative 2 times negative 2 is 4. Negative 3 times negative 3 is 9. Always positive. So then comes the question, what number when multiplied by itself gives you a negative result? The answer is nothing. Nothing real anyway. There's no real number that squares to give you a negative number. It breaks the rules. But mathematicians are stubborn. Rather than stop at impossible, they invented a whole new kind of number. One that lives outside the real line. They called it the imaginary unit. And they gave it a name, defined simply as the square root of -1. It was a bold, almost rebellious idea. They took something that had no solution, and gave it a place in the number system. At first, It seemed like nonsense. How can you multiply a number by itself and get a negative result? What does that even mean? But the imaginary unit wasn't meant to be real. It was meant to be useful, and as it turns out, it's incredibly useful. Take a moment here. Close your eyes and imagine the number line, that familiar line stretching from negative infinity to positive infinity. Every point on that line is a real number. But now, imagine stepping off that line, not forward or backward, but sideways. That's what imaginary numbers do. They extend math into a second dimension. Instead of just one line, we now have a plane, a whole new way to navigate numbers. And when you combine real numbers with imaginary ones, you get complex numbers, numbers with two parts, one real, one imaginary, like coordinates in space, like vectors in motion. These strange numbers, born from an impossibility, turn out to be essential for describing waves, oscillations, and the mysterious world of quantum mechanics. Electricity, alternating currents, the vibrations in your headphones, the way atoms behave in a superposition, all of these are modeled using complex numbers. I might not be real, but it describes reality with stunning accuracy, and that's the paradox. A number that shouldn't exist, a number that breaks the most basic rules of multiplication, becomes one of the most important tools in physics, engineering, and signal processing. It's almost poetic. Something born from contradiction becomes the language of truth. Even the way I behaves is strange. If you square it, you get -1. If you multiply it again, you get -I multiply once more, and you're back to 1. It rotates in a cycle, a loop of transformation. In this way, I doesn't just describe values, it describes motion, rotation, phase. It's a number that moves, that spins, that circles around the edges of the visible world. And yet, we never see I by itself, in the real world. You can't measure I in a cup. You can't find I on a ruler. It's always hiding in the math, beneath the surface, shaping what we observe, but never being observed. It's like a shadow dimension of numbers, a quiet presence, invisible, but essential. And it makes us ask, what is a number? Does a number have to represent something physical to be real, or can it be real in a different way? Not by existing in the world, but by revealing truths about it. It challenges our idea of existence. It reminds us that mathematics isn't always intuitive, that some truths are hidden, twisting in dimensions we can't see, whispering in languages we're still learning to hear. So take a moment now. Let yourself float sideways off the number line, into that space where numbers curve and spin, where contradiction becomes structure, where the impossible becomes the standard. I lives there, not a mistake, not a patch, but a doorway, a number that shouldn't be real, helping us make sense of reality. And now, as your thoughts drift in this imaginary space, a quiet question echoes. If something as strange as I can reveal so much about the universe, what else might be out there? What other impossibilities are waiting, just off the edge of what we think we know? Close your eyes and imagine the smallest thing you can. A grain of sand? A molecule? An atom? Now go smaller, smaller than a quark, smaller than a Planck length, the theoretical limit of how tiny space itself can be measured. Now ask yourself, what if there's something even smaller? Not just a small thing, but a concept. A number so tiny, it's smaller than any real number you can think of, but still greater than 0. Welcome to the paradox of the infinitesimal. The idea of infinitesimals dates back centuries. Long before calculus became a pillar of modern mathematics, philosophers and mathematicians struggled with the idea of change, how a curve bends, how velocity shifts, how anything moves from one state to another. To understand change, you need to understand limits. You need to zoom in, infinitely close, to see how something behaves as it approaches a point. But how close is close? How small is small enough? The answer, for a long time, was the infinitesimal, a quantity so tiny that it wasn't 0, but it was smaller than any positive number you could imagine. A ghost of a number, a whisper of change. At first, infinitesimals were used loosely. Mathematicians like Newton and Leibniz leaned on them to develop calculus, treating them like actual quantities you could add, subtract, and cancel out. They imagined them as slices of movement, infinitely thin threads of time and space. But not everyone was convinced. How could you work with something that isn't really a number, something smaller than any number, and yet still somehow not nothing? It felt like cheating, like using a magic trick to solve problems that demanded clarity. Eventually, mathematicians replaced infinitesimals with the concept of limits. More rigorous, more precise, infinitesimals were pushed into the shadows, considered too vague, too philosophical, but they never disappeared. In the 20th century they returned, this time through something called non-standard analysis, a new framework that brought infinitesimals back into the fold, with rules and structure, not as vague ideas but as legitimate mathematical objects. And still, they remain strange. An infinitesimal is greater than zero, but smaller than any fraction. Imagine a number that, if you multiplied it by a billion, you'd still get something that looks like zero. A number so close to nothing that it's indistinguishable, yet undeniably not nothing. It breaks your intuition, doesn't it? We tend to think in absolutes. Either something exists, or it doesn't. Either a value is zero, or it's measurable. But infinitesimals blur that line. They sit in a liminal space between presence and absence, like the edge of a shadow, or the moment between waking and sleep. Let's pause there. Let your thoughts narrow, like the gap between two mirrors reflecting each other forever. Think of a dot on a page, so small you can't see it. Then imagine cutting that dot in half, then in half again, and again. Infinitesimals live in that impossible space, after every halving, beyond every decimal, nestled in a place numbers weren't supposed to go. But here's the strangest part. These ghostly numbers are essential to understanding motion, growth, curves, and time. Without infinitesimals, or the logic they represent, we wouldn't have physics, or engineering, or simulations of life itself. They are invisible architects. They don't exist in the way whole numbers do. You can't point to an infinitesimal and say, there it is, but their effects are everywhere. Like gravity, like silence, like the beat between heartbeats. And they lead us to a deeper question. Is the universe continuous, or made of discrete steps? If reality is continuous, then infinitesimals are baked into the fabric of existence, the glue between moments. But if the universe is digital, composed of tiny indivisible units, then infinitesimals might be nothing more than mathematical dreams, elegant, but ultimately unreal. So which is it? We don't know. But that's what makes this number so unsettling. It asks us to question not just how math works, but how reality works. And maybe that's why infinitesimals shouldn't exist. Not because they're wrong, but because they show us how little we understand about what's beneath the surface. Like zero, infinitesimals remind us that the absence of something can still carry meaning, that there is structure in silence, that change itself relies on things we cannot see. So tonight, as you let your thoughts drift smaller and smaller, imagine shrinking into a world where numbers become thinner than time, lighter than thought, where the space between two moments is infinite, and yet still contains movement. Infinitesimals live there, quiet, impossible, essential. And now, as we rise gently from the edge of the immeasurably small, we look toward a number that is immeasurably strange, a number that isn't real, and yet is used every day to describe the fabric of electricity, magnetism, and quantum behavior. Picture this. You're in ancient Greece. A mathematician in a flowing robe is drawing perfect triangles in the sand. The world, he believes, is built from whole numbers, ratios of clean, countable values. To him, mathematics is sacred, orderly, understandable. Now he draws a square. Each side is exactly 1 unit long. Then he connects two opposite corners, forming a diagonal. He pauses, and he asks, how long is that diagonal? Using geometry we can find the answer. It's the square root of 2. Simple, right? But when the Greeks tried to write that number as a fraction, any fraction, they found something disturbing. No matter how hard they tried, the square root of 2 could not be written as a ratio of whole numbers. Not as 1/2, or 5/8, or even 1,000,000/1,000,000,000. It wasn't just inconvenient, it was impossible. The number simply would not resolve. It didn't end. It didn't repeat. It defied measurement. What they'd discovered was something deeply unsettling. The first known irrational number. Irrational, not because it was illogical, but because it could not be expressed as a ratio. It didn't belong to the world of fractions. It couldn't be grasped, only approached. The decimal expansion of the square root of 2 goes on forever. never repeating. A trail of digits disappearing into the unknown. Take a moment to let that sink in. This number appears from one of the most basic shapes in geometry, the diagonal of a square, and yet it opens a crack in the very foundation of arithmetic. According to legend, one of the Pythagoreans who revealed the irrational nature of the square root of 2 was thrown overboard at sea. The idea was that dangerous, because if this number existed, what else might exist? The square root of 2 is more than just a weird decimal. It's the first whisper of mathematical chaos, a number that arises naturally, but escapes our ability to contain it. Even today, with supercomputers we can only approximate it. 1.4142, and on, and on. We can get close, closer, even closer still, but never exact, never complete. In math, that's uncomfortable, because mathematics is often thought of as the pursuit of precision, of perfection. But irrational numbers like the square root of 2 remind us that even within that perfection, there are wild, untamable spaces, numbers that can't be fully known, only described from a respectful distance. And yet the square root of 2 shows up everywhere. It appears in architecture, art, and music. It's found in the proportions of paper sizes, in diagonal measurements, and in the algorithms of computer graphics. It's part of the golden thread that connects math to the natural world. And that's the paradox, a number that cannot be measured precisely, but that defines the measurable world. It's almost poetic. This number, born from a square, reveals that even within perfect shapes there are irrational truths, that no matter how carefully we build our models of the world, some part of reality always escapes our grip. Think of trying to measure the diagonal of a square with sides 1 inch long. You take out a ruler, you make the calculation, but you'll never quite pin it down. The more you zoom in, the more digits spill out. The number doesn't want to be caught. It resists. And maybe that's the most haunting thing of all. The square root of 2 exists. It's real, but it can never be written in full. Not with any amount of time, not with any amount of ink. It's a number that's there, but not entirely here, like a horizon you can walk toward forever, and never reach. And so we begin to ask, if this number, so foundational, so obvious, can't be fully known, what else lies just beyond the edges of understanding? Let's pause here, breathe into that space, that feeling of knowing something exists, but not being able to capture it. That quiet frustration, or maybe, quiet awe. It's a reminder that we don't control the universe with our equations. We describe it, imperfectly, incompletely, but beautifully. And sometimes, the most important parts of reality are the ones that don't fit neatly into our systems, that challenge us, that remain forever irrational. As you drift in this spiral of endless digits, you may start to feel untethered. But don't worry, you're not lost. You're just moving deeper into the strangeness of numbers, where logic bends and the unknown becomes part of the landscape. Now, we've explored a number that refuses to be written. But what about a number that's infinitely large, but also smaller than anything you can imagine? Imagine staring into a blank page. Pure white, no marks, no lines. Just emptiness. It's not chaos, not noise, but absence. A clean silence. And yet that emptiness holds incredible power. Mathematically, we gave that emptiness a name. We called it 0. But 0 is not just a placeholder. It's not just the thing you see on your calculator when nothing's been entered yet. 0 is one of the most radical inventions in human history, a number that changed everything by representing nothing. For most of early civilization, 0 didn't exist. The ancient Egyptians, Greeks, and Romans used elaborate number systems, but none included a true concept of nothing as a number. You could have nothing, but you couldn't count nothing. It wasn't until ancient India, around the 5th century, that 0 was born, first as a dot, a placeholder to keep numbers aligned. But that dot became more than just a mark. It evolved into a number on its own, a symbol that didn't just mean nothing there, but the presence of nothing. Take a moment to consider that, a presence of absence. We started to calculate with it, add it, subtract it, put it in the middle of equations, and everything changed. With 0, we could build the decimal system, a place value structure that allowed for mathematics to scale infinitely. With 0, we could balance equations, calculate debts, explore symmetry. Without it, modern computing, physics, engineering, all of it collapses. And yet, zero is not innocent. Zero is a void that behaves unlike anything else. Multiply anything by it, and it vanishes. 10,000, a million, a billion, all disappear into nothingness with a single touch of zero. It doesn't just mean absence, it erases. It also divides reality in half, positive on one side, negative on the other, a boundary with no thickness, no mass, and no location. And yet, everything crosses through it. But division, that's where things become truly strange, because dividing by zero doesn't just break the rules of math, it breaks reality. What happens when you try to divide something by zero? The answer is you can't, not just because it's undefined, but because it leads to contradiction. If you take 10 and divide it by zero, there is no number that, multiplied by zero, gives you 10. Any number times zero is still zero. So nothing makes sense. The whole structure crumbles. In physics, dividing by zero often signals a singularity, a place where laws break down, like the center of a black hole, where gravity becomes infinite, and space and time themselves seem to collapse. At the singularity, the equations we use to understand the universe just stop working. It's not that the answers are hard to find, it's that there are no answers. Zero, then, is a threshold, a doorway between what can be known and what can't. And yet, we use it every day, on clocks, on speedometers, on thermometers. We treat it like a starting point. 0 degrees, 0 miles per hour, 0%. But what we're really doing is marking the edge of something, the line where presence becomes absence, movement becomes stillness, meaning becomes mystery. There's even a deeper question. Is zero something, or is it nothing? It sits on the number line, like every other number, equally spaced between -1 and 1. It has a place, but it doesn't behave like other numbers. It's the only number that's both additive identity and a multiplicative abyss. It holds equations together, and it tears them apart. We trust it, but we don't understand it. And that gives it an eerie kind of power. Think of the universe before the Big Bang. Not darkness, not a starless void, but truly nothing. No space, no time, no matter, a zero state. And from that, somehow, everything was born. Was zero the beginning, or was it just a point in between? Take a moment here, let your mind go still, like water settling in a glass. Imagine that deep, unmeasurable silence, not empty like a room without furniture, but empty like the absence of existence. Zero, not just the symbol, but the sensation. It's humbling, isn't it? That a number we learned in childhood could lead us to the edge of metaphysics. Zero teaches us that absence can be active, that silence can be full of meaning, that emptiness can create structure. And in that way, it's more than just a number. It's a reflection of the limits of knowledge, a mirror of death, and maybe even a hint of creation. So when we say nothing, what do we really mean? Because sometimes, nothing is the foundation everything else is built on. Now, as you drift into the quiet thought of zero, let your mind gently orbit the edge of understanding. We've seen numbers that stretch into infinity, numbers that don't exist in reality, numbers that encode the entire universe. And now, a number that means the absence of all things. But what about a number that isn't real, and isn't even complete? Close your eyes, and imagine a circle. Not just any circle, a perfect one. No jagged edges, no distortion. Just smooth, endless symmetry, from the tiniest atom to the shape of galaxies. Circles are everywhere in nature, but how do we measure one? How do we describe the relationship between its roundness and the straight lines we use to study it? Enter a number both ancient and eternal. Pi. You probably first met it in school. Pi is the ratio between a circle's circumference and its diameter. No matter how big or small the circle, that ratio remains the same. It starts with the digits 3.141, and goes on forever. An endless, non-repeating stream of numbers. Infinite, irrational, unpredictable. But that's just the beginning. You see, pi isn't just about circles. It's about everything. It appears in the equations that describe waves, time, probability, information, and even the structure of the universe itself. Somehow, this strange, swirling number shows up in places where circles don't exist at all. It's in quantum physics. It's in statistics. It's in signal processing, cosmology, and chaos theory. Pi is everywhere, and nowhere, all at once. But what makes it truly haunting is that hidden within pi are the digits of every possible number sequence. If you believe in a certain mathematical property called normality, then somewhere deep inside the infinite digits of pi are the coordinates to everything that has ever happened, or ever will. Your birth date, the barcodes of every item in every store, every password, every song ever written, the genetic code of every living thing, every sentence spoken, every book written, every dream you've ever had, encoded in numbers, buried like fossils inside this one infinite string. Take a moment to sit with that. Imagine the digits of pi unfolding across a long black velvet curtain, never repeating, never ending. Somewhere in that stream is your name. Somewhere the answer to a question you haven't yet asked. Somewhere, a perfect replica of the universe. And maybe, just beyond that, a version of the universe where everything is slightly different. Pi is not just a number. It is a vast hidden library, a cathedral made of digits. And yet, we will never reach the end. Not because we're not smart enough, or not fast enough, but because there is no end. You can compute 1 trillion digits of pi, and still you're just standing at the entrance, like staring into an abyss of infinite complexity. There's a beauty in that, but also a quiet terror. Because no matter how deep we go, we'll never know if what we're searching for is ahead of us, or already passed by. Some mathematicians have spent their lives calculating the digits of pi, chasing its tail through computers and algorithms. But the more digits we uncover, the more it seems to laugh at us, a number that always slips just beyond our reach. Pi is irrational. That means it can't be expressed as a fraction. No perfect ratio of whole numbers can ever capture it. It resists order. It resists reason. It resists being known. And yet, it's everywhere. How can something be so essential, and yet so unknowable? Maybe pi is a reminder that reality isn't always meant to be solved. That there are patterns we're allowed to glimpse, but never fully possess. Like standing in a vast forest and realizing you'll never see every tree, but you're still part of the forest just the same. Let's take a gentle breath here. Now imagine the numbers of pi as stars, each one twinkling in the darkness, forming constellations of meaning. As you drift deeper, you start to see shapes, memories, ideas, possibilities. But just as you reach out to touch them, they dissolve into more digits, more mystery, more math. We live in a world shaped by certainty, by definitions and categories. But pi defies all of that. It is logic without closure, form without edge, a reminder that not everything can be boxed up, tied down, or explained. And perhaps that's the lesson. Not every number exists to be understood. Some exist to remind us that understanding has limits, that we are small, and the universe is not. So the next time you draw a circle, remember that what you're drawing isn't just a shape. It's a doorway, a symbol of everything that doesn't quite make sense, and never will. And deep inside that doorway, forever spinning, is pi, the number that contains everything. As you let this idea settle in your mind, you may wonder, if some numbers hold infinity, what happens when a number describes something so impossible? It erases itself. There's something oddly comforting about the number line. From left to right, negative to positive, it stretches endlessly across the page. 0 in the center, positive numbers marching to the right, negative ones fading into the left. Each number has its place. Everything seems orderly, until, one day, someone asks a simple question. What's the square root of -1? Your mind stalls. You remember that squaring any real number, whether it's positive or negative, gives you a positive result. 2 times 2 is 4. -2 times -2 is also 4. There seems to be no number that, when squared, becomes negative. So what could possibly be the square root of -1? The answer is a number that shouldn't exist. And yet it does. Mathematicians call it I. Not I as in the self, but I as in imaginary. The name wasn't chosen lightly. When the concept first appeared, it was dismissed, mocked, even feared. Imaginary numbers sounded like fantasy, tools of deception, or tricks to avoid the truth. And yet, over time, they became not just accepted, but essential. So what exactly is I? Is defined as the square root of -1. On its own, it doesn't live anywhere on the traditional number line. Instead, it opens up an entirely new dimension of numbers, a perpendicular axis that intersects the real number line at 0. Together, they form what mathematicians call the complex plane. Now, Instead of just real numbers, we can express values as combinations, a real part plus an imaginary part. For example, 3 plus 2i. These are called complex numbers, and they exist not in one dimension, but in two. What's incredible and unsettling is that the imaginary number I, which began as a kind of mathematical outcast, ended up becoming central to some of the most powerful equations we've ever created. It's used in quantum mechanics to describe the strange behavior of particles. It shows up in signal processing, allowing engineers to work with sound and light. It's found in fractals, chaos theory, and even in the formulas used to model electricity. And then there's Euler's identity, a simple, elegant equation involving the numbers e, pi, 1, 0, and I, all connected in a circle of meaning. That I, the imaginary unit, could be part of such a beautiful truth, makes us wonder, how can something that's not supposed to exist be more useful than anything we can see? Take a moment here to reflect on that contradiction. We call it imaginary, and yet it powers real machines. It's not visible, and yet it helps us describe the universe. It was invented, and yet it feels discovered. I doesn't just challenge our understanding of numbers, it challenges our understanding of reality itself. Because if we can accept the existence of a number that isn't real, but is still essential, what else might be true? What else might exist, quietly shaping our world, invisible to our eyes, but deeply embedded in the structure of things? Imaginary numbers also open the door to rotation in the complex plane. When you multiply by I, you're not just scaling a number, you're rotating it. Multiply by I once, and the number turns 90 degrees. Multiply by I again, and it rotates another 90. After 4 multiplications, a times I, times I, times I, you're back to where you started. This rotation, this mathematical dance, appears again and again in nature, in the oscillation of waves, in the spin of electrons, in the heartbeat of quantum fields. I gives shape to the unseen, and maybe, in that way, it's not so different from imagination itself. Maybe the term imaginary wasn't a dismissal. Maybe it was a quiet recognition that some truths are so strange, they can only be held in the mind's eye. We often think of math as cold and rigid, but imaginary numbers remind us that mathematics is also creative, poetic, even. It invents concepts that don't exist in the physical world, and yet describe it more accurately than our senses ever could. And maybe that's what makes I one of the most haunting numbers of all. It shouldn't exist. It doesn't fit into the framework we were given. And yet without it, the framework collapses. You're floating now, through a world of numbers that aren't real, but aren't false either. Numbers that shimmer in that in-between space, not quite visible, not quite touchable, but undeniably there. As you drift through this complex plane, you begin to wonder, if a number like I can exist just by definition, could there be numbers that contain entire universes within them? Let's journey now into one such number. A number so vast, so unknowably long, that even the known universe isn't big enough to hold it. Let's meet the infinite, never-repeating digits of a number that hides all of reality inside its spiral, the one and only, pi. There's a strange hotel on the edge of reality. It stretches beyond your field of vision, with room after room, hallway after hallway, continuing forever. You walk into the lobby. It's warm and quiet. The clerk behind the desk greets you with a nod and says, "Welcome to Hilbert's Hotel. Every room is occupied, but don't worry, we can still make space for you." At first, you think it's a joke. The sign outside said there were infinitely many rooms. But if they're all full, how can you still check in? The answer lies in a number that doesn't behave like any number you've ever known. Infinity, not just as a concept of a lot or beyond counting, but as a mathematically treated quantity. And what you're about to discover is that infinity isn't just big, it's broken. Hilbert's Hotel is a thought experiment created by the German mathematician David Hilbert in the early 20th century. It was designed to illustrate the strange, unintuitive properties of infinite sets. In this hotel, every room is numbered with a natural number, 1, 2, 3, 4, and so on forever. Now imagine the hotel is full, one guest in each room, but then a new guest shows up. Can they still be accommodated? Yes. The clerk simply asks every current guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on. Room 1 is now empty, and the new guest can check in. Despite the hotel being full, it had room for more. This is the first strange consequence of treating infinity as a manipulable value. It defies your sense of logic. Take a breath and sit with that for a moment. A hotel that's full, and yet never actually full. Let's stretch it further. Suppose not just one new guest arrives, but an infinite number of new guests. Could the hotel still make room for them? Yes, again. This time, the clerk asks every existing guest to move to a room that is twice their current room number. If you were in room 1, you move to room 2. If you were in room 2, you move to room 4. And if you were in room 3, you move to room 6, and so on. Now all the odd-numbered rooms are empty. Room 1, room 3, room 5, an infinite number of rooms. And now, the new infinite line of guests can move into those newly opened spaces. Infinity, it seems, isn't just endless, it's flexible, and that's where it becomes deeply unsettling. In our day-to-day lives, numbers behave. If you add 5 to 100, you get 105. If you double a number, it gets twice as big. But infinity breaks those rules. Infinity plus 1 is still infinity. Infinity times 2, also infinity. There are infinities larger than other infinities, and they all behave in ways that don't align with how we usually experience the world. Mathematicians call the type of infinity used in Hilbert's hotel countable infinity. It's the infinity of natural numbers, the kind you can, at least in theory, count one by one. But not all infinities are like that. Some, like the infinity of real numbers between 0 and 1, are uncountable. There are quite literally more real numbers between 0 and 1 than there are whole numbers in total. In fact, there are infinitely more. This leads to something mind-bending. There are infinities that are strictly larger than other infinities, an infinity of a higher order. So the question is, what kind of number is that? Infinity breaks arithmetic. It doesn't behave like the numbers we're used to, and yet it's essential. Without it, we couldn't make sense of calculus, couldn't describe the universe, couldn't talk about black holes or the age of the cosmos. Infinity is the backdrop to so much of mathematics, and yet we can never fully grasp it. Perhaps what's most haunting is that infinity lives in contradiction. It's a number that grows and stretches and contains itself. It's full, and yet never truly full. It's an idea that has shape, but no boundary. It's a number that shouldn't exist, and yet we rely on it constantly. Then so we arrive at the paradox. Infinity is essential to understanding the world, but it breaks the rules we use to understand it. It's like trying to measure the ocean with a spoon, or define the universe using a grain of sand. Take a moment to reflect on that. Imagine checking into a hotel that can always make room for one more. Picture numbers that expand and fold into themselves, never ending, never repeating, always containing more than we can comprehend. Infinity is not a destination, it's a direction. It's a whisper from mathematics that there are truths larger than logic, and questions without final answers. Now let the concept settle in your mind like soft fog. You're drifting through infinite hallways, where every step leads to more doors, more paths, more questions. And just when you feel the corridors might never end, a strange thought occurs. What if some numbers don't just stretch forever, but actually don't belong at all?